Okay, hello everybody. This is Dr. Hasan again in Math, Calculus and Linear Algebra. This is Module 2. The title of this module will be Solve System of Equations and Eigenvalues of Matrices. And the first week in this module, week number 4, we will solve system of linear equation using different operations we already discussed in last sessions, besides some few properties need to be discussed here. So we already discussed determinant for 2 by 2, 3 by 3. We will see in this module also how we will do inverse of matrices. Then we will use the first method, which is Gauss elimination. Now, first of all, I would like to mention highlight, let me say, some properties related to determinants before we go for inverse. Okay, the first property say that the value of determinant remain unchanged if row or column are interchanged. As example, in this one here, you can see that these two rows, row 1 and row 2, changed their places. Okay, or we can change column 1 and 2. We can change both of them. This will not change the determinant. Okay, column 1 and 2, as you can see here, or row 1 and 2, it doesn't matter. This will keep the determinant safe and the same value. Okay, the other one is if we change any row, or any column. The first one could be transpose also, talking about transpose, as you can see here. Okay, will not change things. If we change any row or any column, this will not change things. As example, these two changed. Okay, we can't change any row and any column. This will keep the determinant the same. The other issue, if we multiply scalar by any row or column, then we can't take it as a common outside the determinant, and determinant will not change. Or the same thing could be, say, if we divide any matrix, then determinant will not change. Now, this is extra exercises. I advise you to solve them regarding addition, subtraction of matrices. Keep in your mind, we can add and subtract similar dimension matrices. If there is difference, we cannot do that. For multiplication, it doesn't matter, but we need to make sure that the first matrix column should equal to the second matrix row, as in these examples. Now, also, just to remind you, we discussed the different methods used to calculate the determinant. We discussed cofactor expansion and cross product. Okay, I will mention to the row reduction now in the next few slides. And this is just to remind you that if we have any matrix similar to this one, we can copy the first two columns and put them here as a fourth and fifth column, and then you take the leading diagonals, multiply them and give them positive sign, while the others you multiply them and give them the negative signs, and then you do the math to get the final answer. Okay, we solve a few problems. Any cofactor can be found by using the formula, as I mentioned before, Cij equal minus 1 to the power I plus j minor ij. Okay, example of this cofactor 1 1, it means row 1 column 1. This is row 1, this is column 1. Then minus 1 to the power 1 1 row and column, and the minor, this is the minor. As you can see here, we do the determinant, we got the final answer. We can apply this for any item in the matrix. Okay, now next, in this property, as you can see here, it tells me that if any column or row consists 2 or more items. As example, this column, in this column number 1, you can see item with x, item with y, item with z. The determinant of this matrix can be split into separate items, a 1 2 3 with others, plus x y z with others. The determinant, this one plus this one, will give me the original matrix determinant. another property. If we have any matrix and we add, subtract, multiply, let me say, items of another row or column and add it to the original row or column, this will not change things. As example, now what I will do, I keep second and third column as they are, but I would like to add m times the second column minus n times the third column to the column 1. Is this will change the determinant? No, it will not change the determinant. By the way, I am just describing the theory. Later on with examples, this will be clarified with numbers. Okay. Now, the other property, number 6, if any two rows or columns definitely of a determinant are identical, then its value will be 0. Okay. See here as example, A1, B1, C1, this is row number 1, and number 3 are the same. So the determinant will be 0. Now, the next one is if each elements in one row or one column equal to 0, then this will give the 0 determinant. This is expected because you remember cofactor expansion method. We multiply by A1, A2, A3, right? So if any one of them 0, this will lead to 0 output. Okay. Now, if we have a diagonal matrix similar to this, okay, it means only diagonal have values, then its determinant is the multiplication of these elements in the diagonal. This is directly easy, don't need to go to the methods and apply it directly, just multiply the diagonal elements. Okay. For a cofactor, I explained it before, okay, but just example here to remind you before I go for my point is if we want to find the determinant using cofactor expansion, I use any row or column. So we focus more on rows or columns which have zeros, but let's assume here that I want to find the cofactor using this column. If up to me, I will use the first row or the third column because it contains 0. But let's go with the question. He asked me to find this column. Then I will say, okay, 3 times is cofactor minus 2 times is cofactor, 5 times is cofactor. And we understand what is the cofactor. Cofactor Cij equal minus 1 I plus j mij. We did this formula on each one of them and we do the math to get the matrix. Now another one here with 4. If I would like to advise you, I will say, okay, go ahead with this column. Why? Because we have 0 here, 0 here. This is the most column, the most 0 in this column. Okay. Now also another property, if I have a matrix AB, okay, and I will add, subtract, let me say, multiply another row and add it to this, to one row or another, then what will this lead to? This will not change the matrix. Example, this matrix A, if I multiply A by B using cross product, then I got AD minus BC. This is the results. Let's assume that I will replace row number 2, this row, with row number 2 plus k times row number 1. It means I will make this row is row number 2 plus k row number 1. It means here I will multiply by k and add it. It means b plus ka, d plus kc. Is this will change the determinant? No, it will not change. Let's see. Let's prove it. Multiply this by this here. We are here. Simplify, multiply here and here, distribute to remove the brackets, we are here. Cancel similar items, we are here. Just a minute, these are the same. So this tells me that it's okay to multiply, add, subtract columns with columns, rows with rows. There. Okay, here example how we use this, because I will need it in the next technique. He asked me to find the determinant of this matrix. What I will do, I will change row number 2 with row number 2 minus row number 1. It means I will come you may say, okay, why? Because I can see here there is sort of similarity. Okay, so if I change row number 2, when I change row number 2, it means I keep row number 1 without change, only focusing on row number 2. I will subtract, mean 2 minus 1, it gives 1. 7 minus 7, it gives 0. 3 minus 3, it gives 0. You may say, okay, what is the benefit? Adding zeros in here will make my task easy. Have a look. I come to the determinant. I will find the determinant on this row. Okay, you will say, okay, it is minus 1. Okay, determinant the determinant of the minor, okay, which is 7, 3, 4, 5, as we learned before. So direct one step. Because of these zeros, it make my task, my solution very easy and direct. Okay, now interchange rows, okay, will lead to minus the determinant. How this happen? Have a look. If I have this matrix, okay, A, C, B, D, okay, I interchange them. Okay, BD came here, AC came here. Okay, what will happen? Let's see. The original one is directly AD minus BC, as we learned. But when I interchange them, I multiply here and here. I'm here. Let me rearrange. I want to make similarity. It seems to be the same determinant, but with minus sign. Okay. Replacing row with K times row, it's the same determinant, just K outside. As you can see here, this is the original. We discuss it in different examples now. But when I multiply first row by K as example, and I do cross multiply here, we are here. Take K as a common, the same previous determinant, just multiply by K. Okay. Now, let's take this example and use this row reduction. See this example. What I will do, I will try to zero the 3 here and the minus 2 here. What I will do first, I will, because I want to make column number 1 with many zeros, just one number, then it's easy to find the determinant. What I will say, how can I make this 3 0? You will say, okay, let's multiply the first row by minus 3 and add. So minus 3 by 1, minus 3. Minus 3 by 4, minus 12. Minus 3 by 2, minus 6. I will add. Okay? Definitely, we will keep the same row and the row number 1 and row number 3 constant, but we focus only on